Oh, here we've got a MC, and it's an equilibrium multiple choice question. It's a good one. There's a lot of important information that you should know to be able to solve this type of a problem. And we're starting off with an equilibrium. Here you can see our equilibrium area, arrows, and you'll see they give us an indication of the change in enthalpy, the potential energy for this reaction. They say the reaction is at equilibrium, so this is reached the situation where the forward reaction equals the reverse reaction. Which of the following will decrease? Okay, this is important. Decrease the amount of calcium oxide. We want this reaction to go so that the left arrow, reverse reaction, it goes faster than the forward reaction, using up some of this calcium oxide and CO2. Now we have a number of choices involving temperature, here's temperature, volume, removing substances from this. Well, let's look at this equilibrium expression. Here I'm going to go to the solution, which I have. This is AP13, tab 13, chemical equilibrium. That's used a lot on the exam. And we're going to rewrite the reaction because we want to include all of this stuff. This is an endothermic reaction. We use heat energy to break these bonds, and then these new ones form. These new ones have less, they're weaker bonds. They've got more potential of snapping back together. When you add heat, you basically are separating these atoms a bit more and changing this kinetic energy into a greater potential energy. That's why on a graph, we go up. Potential energy, we've made weaker bonds. We've separated atoms. Endothermic. Now, so we put the heat here as a reactant. Now, the equilibrium expression, where we include all the species, would be this. I'm going to scroll up a little bit so we can see that at the center. I made it a pressure equilibrium, and I included parentheses, which you use with pressure, and partial pressures, the pressure of each one of these. The pressure of the calcium oxide, the pressure of the CO2, and the partial pressure of the calcium oxide in this container. So we imagine a container, and we scroll the container down here, and we've got carbon dioxide, calcium carbonate, and calcium oxide. Now back to our question, and by now I hope you should be saying, oh, wrong, 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 because this seems sort of silly, having a pressure of this solid, and it's a pure substance. And this is where we go back to this. This is our AP13 summary, and here we've got the AP13 chapter 14 equilibrium in boldface. Do not include solids or liquids in the equilibrium expression. I'll come back to this later, and I use this as an example. I'll explain why later, but let's just make sure we follow that instruction. And pure solids or concentrations, the pressure of these things don't change. They're constant for a given temperature, and therefore, because these pressures of pure substances, solids and liquids, don't change, we don't include them in the expression. They're not going to change at all. You can't change them. So all we've got is the pressure of CO2 is going to be whatever this equilibrium constant is, period. You're stuck with it. I don't care how much calcium oxide you have or calcium carbonate. Back to this image again. Let me run down here. Now here we've got a small pile of it. It's got no dealings with in terms of changes, whether it's small or large. If it's a pure substance, I don't care how much you have of it as a solid, it's going to have the same effect in terms of an equilibrium. So we can basically ignore these devices. We can ignore the solids because they're not going to change our pressure. Let me get back here. So that's it. We're stuck with it, but the question says we want to decrease the amount of CaO. We want to have less of this solid. how are we going to do that in an equilibrium? Well, that's where we get back to our heat. The only way to shift this equilibrium is to change the equilibrium constant. And we've got our heat in here. So if we decrease this amount of heat, we can shift the equilibrium by lowering the equilibrium constant. On an endothermic reaction, if you end up decreasing the temperature, you end up having the reaction go backwards. You drive it forwards by heating it. So if we decrease the heat, the reverse reaction increases, and in fact, really we're decreasing the temperature. This is a Le Chatelier trick. The reaction will go backwards and we'll have less calcium oxide. As I say, this is sort of a trick. This is really the cause of this is the difference in the activation energies. But that's the answer to our problem, and we have to be very careful and remember that we don't include solids or liquids in our equilibrium expression. Now, I do have an exception here, and this exception has shown up once on the AP exams, and we'll deal with that a little bit later. But let's go back to our calcium oxide that we have. It's an important reaction. I mean, you undoubtedly are within a couple of feet of the result of this reaction. In fact, your bones are involved in this too, because this calcium oxide is used in making cement. I mean, if you have anything made of cement around you, it was produced by heating up some calcium carbonate. Now, there's calcium carbonate all over the place. Like I say, it's your bones, it's shells, it's mountains. And if you heat this calcium oxide, you will end up shifting this reaction forward to make the quicklime. And in fact, what they'll do is they take limestone or shells or bones even and heat it in a rotary kiln. This thing keeps rotating and rotating, and you make calcium oxide and CO2. Now, this reaction does have a problem environmentally. Not only are you making CO2 from limestone, but also you're using a lot of fossil fuels to get this to a high enough temperature. These rotary kilns run at 1,000 degrees Celsius. So they use huge amounts of fuel to make this calcium oxide, which is then used to make concrete, mortar, and so they're trying to find alternate ways of making calcium oxide. One interesting thing to note, and that is at room temperature, the vapor pressure of here in this diagram, they're showing a pressure pushing this mercury up, but at room temperature, this pressure is minuscule. In fact, at 500 degrees Celsius, the temperature of a candle, the pressure that's produced by this reaction is only 5/10,000ths of an atmosphere. Well, this is good because otherwise we'd have limestone everywhere evaporating if it had a high vapor pressure at room temperature. I mean, our mountains would evaporate, our bones, our teeth, shells would evaporate. The only way you can get it to evaporate considerably, and I notice when we finally get to about 900 to 1,000 degrees, the vapor pressure becomes significant and you can get this calcium oxide. So, and when you see any cement around you, you can imagine the furnace that was required to make the calcium oxide that's used in making that cement. So there's an important feature. Calcium oxide, if you add heat to it, it's going to disintegrate. All the calcium oxide, the limestone, minerals that you see around you couldn't be volcanic because they would have evaporated. They're all deposited by little seashells and such. Chalk and calcium oxide limestone are the result of non-igneous geologic reactions. Okay, one extra little thing. I'm glad you came around because there is an exception to not having liquids in an equilibrium expression. And it's sort of a strange one, and I think the College Board was wrong in doing this. In this question that they had a non-aqueous system, an alcohol solution, and there's some water in it. So this water isn't pure. It's an alcohol, and they should not have used this liquid, but I can't argue with them. Well, I did. I said, your question here is worded poorly. they said, well, it's too late. We've already graded this question. We can't do anything about it. Anyway, the choices, there's only one choice with this. If you have an alcohol solution, you can change the concentration of water because it's mostly alcohol with water as a solvent. And in this reaction, you've got a cobalt hexa aqua complex, which is a pretty pink. If you add enough chloride to it, like concentrated hydrochloric acid, or if you add heat it up, this is an endothermic reaction. If this is a this is an endothermic reaction. If you heat it, you'll push and make this blue, which is this reaction. In this case, they had a situation if they added some water, increased this, and changed this from blue to pink. So our one exception is you have to watch out for water in non-aqueous solutions. Okay, that was an MC and a long explanation because I wanted to tell you about limestone and why it doesn't evaporate.